In this video, I'm going to be presenting about the group project that we did for EC 101 Winter 2024. It's about the frequency-selective musical light show using Fourier transform. So we're going to talk about what is sampling, Nyquist rate, and how do you convert a CT signal to become a DT signal. And then we're going to talk about fast Fourier transform because that's the algorithm that we use for the project itself. And then we're going to go through an example of how we mathematically convert a CT signal to a DT signal, and then we get the output. Okay, so let's start with the theory. So sampling. So the whole idea of sampling is that we want to convert a CT signal to a DT signal, and also vice versa. So in this block diagram, we can see that using a microcontroller, which is the ESP32, we run it through a ADC, a analog to digital converter. And then the ESP32 will do some signal processing stuff in there. And then to get the output, we run into the DAC, the digital analog converter. So the DT signal, the XD of n, is often obtained from predicate sampling of the CT signal. And so you choose the sampling period, the T, and you sample it, you plug in n of t for each of the ends. And that's where, and plugging in that, you get the XD of n. And so that's the sampling period. And then the sampling frequency, and that's related by the usual way, like 1 over t is you get the frequency. And to get the sampling, and also as you get the sampling frequency in terms of like the radians per second, it's just different units, but that's another way of saying it. But we usually use the omega as the radians per second one. So sampling speed. So the sampling speed determines the signal's frequency range that can be represented in a digital waveform. So this range is called the bandwidth. So that's the jargon. And so if you want to represent a signal that has a broad range of frequencies, and you have to have a high enough sampling rate, and thus have to avoid like aliasing. So in fact, the maximum bandwidth of the sample waveform is determined exactly by its sampling rate. And this is exactly what the Nyquist rate is saying. So to avoid aliasing, which is basically to avoid that the copies of the signals, to avoid them being like overlapping, that means our sampling rate has to be at least greater than twice of the highest non-zero frequency, which is stated here. And so why is that? We're going to see it in an example later in the slides. So here's kind of like the rough diagram of why is that the case. Okay. And so how do you process a CT into DT and then back to CT? So this is kind of like the block diagram. And so you have the continuous time signal, you convert it from C to D, and then you get the XD of n, and you run it through the DC system with a certain frequency response, and you get the output, and then you want to convert it back to the continuous time version. So that's the whole idea. And so step number 1 is you convert it to XD of n with sampling period t, and you filter out the XD of n, and you converted that to the Fourier transform. You get XD of j omega, and then you run it through a frequency response. You get the output of that, and then you convert it back to the constant version. And this works if the continuous time signal is band limited. That means you have the highest noise non-zero frequency. In general, this doesn't always work because you cannot determine the highest sampling rate, but we're going to look at the case for band limited. And so the first step is from continuous to discrete conversion. And so we're going to use something called an impulse train, which is denoted here as P of t. And so the xp of t is obtained by multiplying xc of t with p of t. And p of t is basically an impulse train. And so like the name implies, is just a bunch of summations of delta functions shifted by some sampling period, the sampling period itself. And so to obtain the Fourier transform of the xp of j omega, you use the Fourier transform properties that if you multiply in the time domain, you convolute in the Fourier domain, in the frequency domain. to get this. And then the pj omega is determined by this. We derived it in class. And so you convolute that at xj omega, and then you have the 1/2 pi in the front. You get this. And so there's that. And then to convert it from the xp of j omega to become the xd ej e to the j omega, you just rescale the x-axis. So instead of, so let's see the bottom part here. And so if you say, let's say the xc j omega is that triangle wave with the maximum frequency w, big W, and the xpj omega is gonna be a bunch of copies of that, but with the amplitude shift scaled by 1/t, and then the copies are centered at 0, and then all multiples of 2 pi over t. And what the last step is doing is basically scaling all the x-axis by t, and so all the centers of the copies is gonna be all multiples of 2 pi right here. And then let's say this is w, this is w, then actually let's go here. This is w, and this is 2 pi over t. This is known as the sampling frequency, omega s, and hence this is omega s minus w, right? And so to avoid aliasing, not overlapping, then we require that omega s minus w is greater than w, and so hence omega s is greater than 2 times w. And this is exactly the Nyquist rate. So we derived the Nyquist rate from this diagram. That's great. Okay, moving on. So we got the xd ej omega, and to get the output signal, we just multiply the frequency response with the xdj omega, and that's pretty simple to do. And then now you get the output. You want to convert it back to the conversion to the impulse train of that, and you're just doing basically the reverse of what you've been doing. So you convert it back, you get the ycj omega, and because you have a bunch of copies and you want to just obtain just one of the original one, you just run it through a low pass filter to just sift out the copy at the center, and hence you get the continuous time signal. Okay. So we're gonna move on to discrete Fourier transform. This is not to be mistaken with discrete time Fourier transform. This is discrete Fourier transform. That means the samples, it doesn't run from like negative infinity to infinity. We have like discrete number of samples. Hence it runs from 0 to n-1 as the number of samples. It looks very similar to like normal Fourier transform, like normal discrete time Fourier transform, which is different. The range of the number of samples, not infinity. And so that's the normal analysis equation, and then you have the normal synthesis equation. And also, just because this is a discrete time, it's periodic with n. And the runtime of this is O(n) squared, if you can be speaking in computer science lingo. And so the thing about discrete Fourier transform is that it's computationally demanding, because O(n) squared is pretty a big runtime. And is there a better way to do it faster? So let's say we split the DFT into even and odd index subsequent sequences. So you have 2m and then 2m plus 1, where m runs from 1 to n/2 minus 1, so like half of it. And so we split those up, and then we just plug in there, plug in the equations. you split it up, and then you rearrange, do some algebra, you sift out, you pull out the e to the minus j 2 pi k over n to the outside, and then what you notice is that this term is basically the even part of the x of k of the original function, and this is the odd part of that. And so you can do this on and on, and so let's say you just do it the first step. From on squared, we reduce it down to on squared over 2 plus n. So asymptotically it doesn't really affect, but we reduce it down by half. And so if you keep on doing this using the divide and conquer approach, the runtime becomes this is the recurrence relation. So 2 times the new DFT, this is the new DFT algorithm, n over 2 because you keep dividing by half, and then plus O of n because you have to combine the even and odd part. And then using the master theorem, because this is like a suitable master theorem recurrence relations type, you get n log n. This is because it's a steady state recurrence relation. You get n log n, which is pretty fast. It's faster than n squared, and this algorithm, which is a divide and conquer algorithm, is called the fast Fourier transform because it's faster than just normal discrete Fourier transform. Okay, so we're gonna go through this pretty quickly. The example problem. So consider a continuous time signal with that frequency, with that Fourier transform xj omega is a inverted triangle from -1 to 1, and then let the dt system has the frequency response of that shown here in the graph, and then it repeats every period t, and so this goes on forever. And then a CT low pass filter HLP of that, and this has height of t, and assume we say the sampling period to be 0.4 seconds, and so we want to find the final output signal yc of t. So how do we do that? Well, first we're gonna find xpj omega, right? And we saw in the previous slides that xpj omega is just the sum from negative infinity to infinity 1 over t xj omega minus k omega s. So you just kind of like take the original signal and then shift it, like make a bunch of copies centered at 2 pi over t, and you also scale it down by 1 over t, which is 1 over 0.4. And so you got xj omega. You wanna convert it to xd ej e to the j omega, which is just scaling the x-axis to multiply by the sampling period, and hence we should get that all the copies are centered at the multiples of 2 pi, but the amplitude are not affected by that. So that's, and now you multiply the xd ej e to the j omega by the frequency response of the dt system. That we specified that the frequency response to be that kind of like top hat triangle right there, and so the multiplication is going to be pretty ugly looking, and then we find that the signal is gonna look like that type of like a bird. And then after you obtain the ydej omega, you're gonna run it through a low pass filter. No, you're gonna convert it to ypj omega, and so you doing the reverse. So now you dividing by t, and hence the sensors are 2 pi over the sampling period, and then you also run it through low pass filter. The low pass filter has this graph, and then like I said before, we're just sifting out the one copy at the center, at the origin, and hence we get the final signal, which is this ycj omega, and then to get the original signal in the time domain, we have to do inverse Fourier transform, which is kind of tedious, and hence a bunch of tedious calculations, and then we get the final answer, which is to be t squared sine t over 2 plus 8 sine t over 2 minus 4t all over 2t cubed. So that's how we convert from the CT input signal to discretize it, and then write to the DT system, and then convert it back to the output signal. Okay. Here's a list of references. And so let's go into the project itself, the Frequency-Selective light show. And so here's some of the important parts of the code. So the code is, we're going to use a Arduino FFT library. We can code it using the divide and conquer approach, but if there's no library for us, then we're going to use it. And so we gonna initialize the object Arduino FFT, and we're gonna make two arrays, one to store the reals and then one for the imaginary part of signals. And we have three functions that we're gonna talk about. So the FFT windowing is basically to let's say you have if your signal has a non-integer cycles, and it's gonna have like spectral leakage, which we want to avoid, or we want to minimize, and that's what windowing function means. And we're not going to be diving into a lot of detail, but that's basically to minimize the spectral leakage. And then the second function, the FFT compute, that's computing the actual fast Fourier transform using the Kluge algorithm. And then the last one is complex to magnitude, is converting the complex numbers to get the magnitude of the complex numbers obtained. So that's basically it for the FFT algorithm itself. To processing the frequency, again, you're taking the magnitude of this, but since in the code you can see that we initialize all the V imaginary parts become 0, so don't think this part of the code is really necessary, because anything about 0 is just 0. But so the magnitude of this is just the magnitude. It's just A, and this is just A, this is just A. But we're just including that for completeness sake. So this assigning each frequency to its corresponding range. So it's depending on the range of the frequency, we choose whether or not we want to have the red, the green, or the blue lights go off. And so this is the demonstration. This is the circuit, and then we have two videos to simulate, to kind of show how this thing works. So that's it, the end of the video. I hope you learned how sampling works and how cool the FFT algorithm is, because that's one of the most important algorithms in the 20th century, and how that algorithm can be used to make a cool project like this. So thanks for watching.